Well done, my people. So today we will talk about chemical combination. So before we go start, we get some factors we will consider for chemical combinations before chemicals will combine. First, you go need to understand wetin Bohr model, Bohr atomic model mean. So we need to understand metals, they react with non-metals. Metals no dey react with metals unless in the case of alloy, formations of alloy mixtures. And of course that is not reaction. You understand? So, but non-metals they react with non-metals in some situations. But e get some factors wey we go consider before you go know whether this thing go react or not. And they like use Bohr model, and then they like use sub-levels of atomic electronic configurations, and they like use Bohr model. Okay, let's consider this. The first factor we'll consider now the number of electrons in the atom shell. All right, let's see this. This is lithium, right? So this is lithium. Lithium has one electron in the atom shell, and every element they won't get complete electron, which is 8. This guy get two options. Is either we find them go see 7 electrons to complete 8, or we remove this guy, that and somebody. So this guy will be eager to remove 1 instead of getting extra 7. So this is the metal, lithium. Now let's consider this. So this is a non-metal. This guy gets 7 electrons for the atom shell. This guy gets 1. So these two and these two, they're very, very compatible. This is a non-metal and this is a metal. These are case. Now let us consider, we get situations where, you know, if two boys, they live together, one person get to be like woman, while the other one they behave like man. For peace to reign, metals get level by level. And we get some things where they decide whether metals senior this one or this one senior this one. Okay, let's consider that. We get atomic radar. Atomic radar are one major formula, major determinant, and the number of electrons for the atom shell. All right, let us see this. This. Alright, let me consider this. Alright, this is a metal, this is a metal. This guy will give out 3. This guy will give out 1. Now this guy will be ever ready to give out 1. Before this guy will get energy when we use give out this 3. This guy will give out this 1. So this guy, they more positive than this guy. You will believe everything no good than this guy. You understand? Now let us look at this. If we get this kind of metal, this guy, they both get 1 in the atmosphere, but we get atomic radar. That's the distance from the nucleus to the particular atom we will talk about. You see this atom, this element, this electron. You see this electron? It goes very far from the nucleus. It's just like a magnet. If you put iron filings around here, this guy will experience more energy than this guy. So this guy is very, very far. So this guy can easily fall out than this guy. So this guy will get more attraction. So you need more energy before this guy will deliver. So therefore, this guy now senior one to this guy. Because this guy will really deliver. You know what metal they always give. So this guy will readily give because he needs lesser energy to do this job than this guy. You understand? So we will now check how two metals react, two non-metals. So if this is the non-metal and this guy this is also a non-metal. This guy needs 2 to complete. This guy needs 1 to complete. So the both are ladies, they need to receive. But this guy needs only 1 to receive. Why this guy needs 2? It's just like when you get 1 million Or let's say you get 100 naira and a car costs 100 naira. You want to buy a car. Maybe you can't lose 1 naira, you can't get 99 naira. You will then very eager to find this 1 naira than person where just get 50 naira, where still they need more 50 naira to complete. So this guy will be very, very active to receive. So this guy is more electronegative than this guy. This guy is more electronegative than this guy. We will go through understand that. Okay, coming back to our binary compounds. We get 2 things we will consider to know whether 2 elements have 2 elements produce 4. That is valency and oxidation state. So students they confuse oxidation number and valency. They're not the same thing, my brother. Oxidation number now the number of electrons when element will give or receive. For example, let me differentiate these two. For example, let's say I will like use electronic configuration for this. Use 1s, 2s, 3s, 4s, 5s, 2p, 3p, 4p, and 5p. This 3d, 4d, this 4f, this 3d, 5d, 5f. So this is the order. You will understand. I will separate them so you will really understand the difference. Maybe you confuse yourself. Okay, so for oxidation number, let me take this 1s2, 2s2, let's say 2p. Which element is this? Let's say 2p3. This he has not blue. This is not Joji. Alright, let's use this. I want to use something very cheap. I want to use something very, very cheap. No, this is 1, 2, 3, 4. One, two, three, 4, 5. 1, 2, 3, 4, 5 is 4. Then 5, 2p, 1. Alright. So let's look at this. You know your hinge rule. Your hinge rule says before you go to fill, you go first fill all the orbitals before you begin to fill other ones. Okay, this is 1s. I'm going to carry 2 electrons. 1s. This is the first level. 1s2. You get 2. This is 2s. 2s2. This guy gets 2. This is 2p1. This guy gets 3 places. 1, 2, 3. Alright, you go carry 6. So if we fill this now, we go first fill this one. We will fill this one. We will fill this one. We will never fill anymore. So this guy now, this element get only 1. So this element, if this guy goes into reaction, what if this guy go do? We say, he will release this thread. You understand? So if this guy releases this thread, which is this? Excuse me, this is 2p, this 2p. They get the same. They get the same level. So the feelings will be saying this guy will release 1 for this guy to this other side. So this is 1, 2, 3. Because this is 2, this 2. So they are the same level. So according to this 2 is saying you go fill up first. All the levels go then fill before you begin the double up. You understand? So if we fill out, this is 1, 2, 3. This is 1, 2, 3. So the oxidation number of this guy is that he's going to release 3. You understand? So when we release 3, that means it's going to give out 3 electrons. Remember, the number of electrons and the number of protons are the same. So if this guy gets 1, 2, 3, 4, 5, this is 5 electrons, and he will get 5 proton 2. 5 proton 2. You understand? So if you give out 3, what will happen? We don't give out 3. This is minus, 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 minus. 1, 2, 3, 4, 5. This is plus, 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 plus. And remember, if you give out plus, now negative, which is electron, you give out. So if you give out this electron, 3 electrons, what will you do? 3. So now negative 3. So this is the oxidation number of this. Now let us now come back to valency. Valency is not they get negative sign or positive sign. Valency is not they get negative sign, is only positive because there is no way you release. So the valency of this guy is 3. Not because it can give out this 3, but because it has 3 electrons ready to work. Alright, so this is the difference between valency and oxidation. Let me get a compound that one element will get negative valency, a negative oxidation number, but positive valency. Let me give you an example. That is oxygen. If you get oxygen like this is oxygen. So what the oxygen will do? You see, remember, they get 8 electrons and 8 negative and 8 positive. This oxygen. So what the oxygen will do here is that I'm going to collect extra 2 electrons, which is making this place what? 10. So if you balance this thing, you will see something will remain at -2. You get? So this is the oxidation number of oxygen. But this is not the valency of oxygen. The valency of oxygen, now if you consider this, how many, if you consider, I really get valency from this. Look that which is 8, we have 1, 2, 2s2, 2p what? 2p what? 4. Alright, so if you get 1s, this is 1, then you start filling this one, 2s, which is this, and 2p. So you fill 1, 2, 3, I'm filling 6. 1, 2, 3, 4, 5, 6. You get it? So this, you get 2 electrons ready to unpair. The number of 10Q, the number of unpaired electrons, that is valency. You get it? And you go see some people, some element they get like 2, 3 valency, 2, 3 oxidation number. But valency and oxidation number will be the same. Okay, so if you don't understand, you put the video later. Alright, now let me now pick two confusing elements we will combine together. So you will see how this thing will work. So you will clarify God. Okay, let's take carbon and oxygen. Let's take carbon and oxygen. We are going to take carbon and oxygen and iron. Let's just take iron and oxygen. Alright, let's see how this thing will use combine. We'll see the wonderful miracle now. So for carbon, for the combination, when 2 things they combine, we will use the valency, not the oxidation number. The valency. So for carbon, first of all, you get 3 things where you need to know. Before you go combine this thing. First, the number of the symbol of the element. Carbon now C. We are starting with this. And oxygen. The valency. Carbon gets 4 or 2, while oxygen gets 2. And explain this. When we get how carbon get 4 or 2 valency. Carbon number 6. So we get 1s2, 2s2, 2p, 2p2. Okay, so this is for carbon, and we want to take how carbon has 4 and 2 valency. So this is 1, 2, 3, 4, remaining 2. 5, 6. So situations like this is situations, this guy, they dey rare to happen. Because every element won't get a stable state. So this guy, remember his rule say you go first fill everything. So this 1, 2, 3, 4. You understand? I waiting. Now carbon will easily do this thing because they would prefer to they have filled than to get some part filled and some part. You know the balance. So this carbon will prefer to fill everything half. You understand? But some situations they happen where carbon will prefer to keep this one here and have 2 here. So this is valency of 2 ready for bonding. This is 2. And the other way we went through this one, that is 4. So that's why carbon has 4 and 2. Shady boy, you get? You understand? So that is it. So for oxygen, you already know. Oxygen at 8, we have 1s, 1, 2, 2s. It is 1, 2, then 2p, right? 2p1, and one get this thing. 1s2, 1s, 2s, 3, 4s, 5s, 2p, 3p, 4p, 5p, 3d, 4d, 5d, and 4f. So we use our way. Alright. So this is 2p for oxygen. 1, 2, 3, 4, 5, 6, 7, 8. You understand? So this is 2. There is no way when you arrange this in where you know going to make 2. That is valency. Alright, so that is it. So now to combine them, we get carbon and oxygen. So for carbon and oxygen, you put the valence where you use. The valence where you use. This is the valency of, let's use the valency of 4 first. Valency of 4, if you are using carbon with valency of 4, and this will be, you go cross multiplier like this. So carbon will go with 2, while oxygen will go with 4. Of course, when you don't get something like this, you go divide them to where you get common ratio. This 2 to this, you can see that it goes down to 1. Then this 2 to this, you have 2. So this is carbon 4 oxide. That 4, and because the carbon, they use this. That 4 where you see, carbon 4 oxide, is as a result of the valence that carbon is using. Now, what if carbon use this 2? If carbon they use 2, this go to, so it will be like this, C to 2, and go to this. So you can bring down this, you have 2 to 2 is 1, so that's C. So this is carbon 2 oxide. Of course, these 2 will come from the oxidation, the valence we carbon use for this reaction. Alright. So let us now check for iron. Iron, you can see the same thing. You see iron 3, iron 2. Iron will get 2 valence. Atomic number of iron is 26. If we check from here, we get 1s2, 2s2, 2p6, this is 10, 3s2, 3p, what? This 10, 12, 3p, we get 4s, 4s2, is it complete? This is 10, this is 10, the next 6, which is, so we get 3d, so 3d6, 4, 1, 2, 3, 4, 5. Alright, so for iron gets 3 and 2 valence. So first, you know, we have to start filling from the D first. For transition element, you fill the D first and make sure the D is satisfied before you move to S. So this is 3D, 4S2, normally. So this is 1, 2, 3, 4, 5. So if you start filling it, this D, these 2, most times, have to gain energy to this other side. So it falls down to this other side. It falls down. So we have 1, 2, 3, 4, 5, 6. Plus these 2 electrons, 7, 8. So we have 2. So you see that this is 2 valency. So this is 2 valency. We have 2. So alright. So we have 2, and this is 2 valency. So this means that there are 2 unpaired electrons. Alright, so now the case, this is the case where iron has 2 valency. The case where iron has 3 valency. This is what really happened. This is D. This is D. Because it is D, iron first considers D have 1, 2, 3, 4, 5, 6. But it's not okay because this is not balanced. It tends to we go try make him fill up everything. So make him fill everything half, to get balance. So if you fill everything half, get balance, this guy will go. So iron has 5 now in the D orbitals. Then this guy has enough space to fall back. Then this guy will now fall to 6, 7, 8. This is, we don't lose 1, 2, 3, 4, 5, 6. So if you lose 1, 2, sorry. So if you don't lose 1, that is 5. Then we get 1, 2. So we get 1, 2, 3. This is our free electrons. Alright. So this is what will happen. But this iron train does not only occur like that. When they likely occur, and for all, when you them into inside environment, we will get iron train. So that is it. So for iron train, we get iron if it's using train, and this one 2 oxygen. So if you cross, we get iron 2 and oxygen this. So this is what is the name of this iron? This is iron. This iron 3 oxide. Iron 3 oxide. So if we get the case of iron using the valency of that 2, we get 2. We get 2 here. So we will go 2. So we have iron. This to this we have 2. Then this to this we have 2. So this can go on. We have iron. This is the positive capital iron. So we have iron. This. Good. So this is what? This iron 2 oxide. Hope you understand. So don't forget to follow us for more videos in case you don't get anything. If you talk, tell us the topic where you want to help you do it. You don't understand too much.